Problem 34. Determine whether or not the function x cubed minus x squared minus 2x plus 1 has a 0 on the interval from 0 to 2. First thing we'll do is evaluate the function at both endpoints of the interval. So let's call this h of x. We want to look at h of 0 and h of 2. Plugging 0 in for all the x's gives us y equals 1. Plugging 2 in for all the x's also gives us y equals 1. Here the intermediate value theorem doesn't help because y equals 0 is not between these two y values. However, this doesn't mean there isn't a 0 in the interval. What might be happening is if we plug in x equals 0, we get y is 1. So here's our first y value. Then if we plug in x equals 2, we also get y is 1. We don't know if the function dips below and back up, or whether the function stays up throughout the entire interval. We could be in either of these two scenarios. So what we'll do first is look at the derivative. We'll determine whether or not the function is strictly increasing or decreasing. So if we take the derivative of our function, we get 3x squared minus 2x minus 2. And I can't tell just by looking at this whether the function is increasing or decreasing. So let's set it equal to 0, see if we can find the minimum. So setting this equal to 0, I don't see an obvious way to factor this, so let's use the quadratic formula. So we've got x equals 2 plus or minus the square root of b squared, which is 4, minus 4 times a times c, which is negative 24, all over 2 times a, which is 6. And if we simplify this radical and reduce, we get 1 plus or minus 7, radical 7, over 3. And if we look at the results we get from this, we get 1.215 approximately, and negative 0.549. Now remember, we're looking just strictly in the interval from 0 to 2, so we don't want to look at this x value right here. Now we may have a minimum or a maximum at x equals 1.215. Let's determine whether this is a max or a min by testing our intervals. So we're looking at in the interval 0 to 2, we have a critical number at 1.215. Let's plug in an x value to the left, maybe x equals 1, and an x value to the right, maybe x equals 1.5. And we'll plug each of these into the derivative. So if we plug in x equals 1, we get a negative value, indicating that the function is decreasing. If we plug in x equals 1.5, we get a positive value, indicating the function is increasing. So this looks like a minimum. So let's try plugging this into our function. Let's look at h of 1.215. And evaluating this, I see that this is approximately negative 1.113. Now this is below y equals 0, so it's more like this blue picture here, where our y value is down here. Since this is below 0, 0 is between these two y values. That says, by the intermediate value theorem again, there is some number, c, I'm going to call this c1 because it's in this first interval. This is between 0 and 1.215, so that our function h of c1 is 0. That's what the intermediate value theorem guarantees. So there is a root in this interval. And also, if we look at the interval on the right-hand side, between 1.215 and 2, there's a different c value. There is also, I'm going to call this c2 because it's in our second interval. There's a number c2 between 1.215 and x equals 2, so that h of c2 is 0. So what happens here is we have one root in this first subinterval and another root in the second subinterval. So we're asked to determine whether or not this function has a 0 in the interval 0 to 2, and in fact it has at least two roots.